Yeah, so last time I talked about the neural tangent kernel, which is a kind of linear approximation of our neural network if we are looking on very wide nets where the size of the intermediate layer goes to infinity. And yeah, we saw that with this thing we have a nice kind of linear description, but of course this relies on the fact which I mentioned last time, namely that this probabilistic kernel in the limit gets deterministic, and also even more important that it's getting time independent. And that its eigenvalues are bounded away from zero. And so maybe I should say a few words about this, just to give a kind of idea why such things can be true. Not a totally rigorous proof, but at least talking a little bit about this. And so let us look again at the model we are considering, and yeah, maybe with some simplifications. Okay, so the model is we have a function, our neural network, which depends on some parameters, which I call theta. And this is given by a vector A, and this is multiplied with sigma applied to Wx. So x, so this is a function of x. X is our p-dimensional data. This is a matrix, and this is a vector. Okay, and last time we looked on the situation that we wanted to train both A and W, and maybe the main focus is maybe on W. I mean, if W is fixed and I just training A, this is just linear regression. Okay, so the main thing is W. So maybe now I fix A and just look on the behavior on W. And maybe if I want to talk about asymptotic limits, I should also take care of the scaling, which I more or less ignored last time. So in here I should also scale with 1 over m. So m is the size of our features. So W or A is an m-dimensional vector, and W is a p times m vector. Okay, and then last time I already wrote this in a form that essentially I decomposed this matrix W into a vector where the entries of the vector are given by other vectors. So I mean I write a matrix as a vector of vectors by just collecting the row vectors. So yeah, I write this, and then this here, okay, this is the inner product. I mean, this is the inner product between the entry of this vector and the corresponding row of this vector. So I can write this as 1 over square root of m sum from 1 up to m ai times sigma of Wi transpose x. And this capital W I have written as a vector where the rows are vectors by themselves. Okay, good. So this is now an inner product here. So everything here is scalar. Good. Okay, and now I want to optimize now over the W, which means over those Wi's, and I keep the A fixed. So my parameters, which I consider here really as parameters which I'm going to change, are just the entries of the W. Over the W, and I keep the A fixed. So I choose this in the beginning maybe in a random way, but I'm not going to do optimization over this. So this means my theta is just the collection of the W's. Good. Okay, and then of course, yeah, I should now also be precise about the normalizations. So the AIs, I mean, usually I take them as Gaussian vectors, but now I just take them as plus minus 1, just to make things simpler, because at some point I get the square of them, then it's good if they are just plus minus 1, then they will disappear, and essentially it doesn't make a difference. Okay, so the normalizations which I choose, so the AI I choose uniformly just from -1 and +1. So you're just taking on two values. But AI is an m-dimensional vector where the entries are ±1 chosen in a random way. And this means, of course, that the norm of this vector A is of the order 1. Yeah. Actually, together with this 1 over square root of m. Okay, so I mean that's so this 1 over square root of m. This makes this yeah, this makes this of the order 1. Good, okay, and then the W's we are choosing as standard Gaussian random matrices, and yeah, they are normalized such that their variance is equal to 1. So W is just a standard Gaussian random matrix, and so this means each Wi is just a Gaussian vector, Gaussian random vector. So Wi is just a normal distribution with mean 0, and the covariance matrix is the identity matrix. Okay, so this just means all entries are independent and they have variance 1. Yeah, okay. And okay, we also assume that the input data, this vector x, this has a norm 1. So we consider, I mean, this is a function of x, but essentially I'm restricting two elements on the unit surface. So I assume in the following also that x is of norm 1. Good, okay, and then in this setting we looked on this kernel last time, which governs the evolution of the parameters. And last time, I mean, we did optimization with respect to A and with respect to W, and this kernel had essentially two terms. I mean, this kernel is essentially the gradient multiplied with itself. The gradient of the function with respect to the parameters. Last time I had the gradient with respect to A and the gradient with respect to W, and the gradient with respect to A is now just missing. That was the simpler part. I mean, I'm leaving out the simpler part, concentrating on the gradient with respect to W, which is really the interesting part now. Okay, so this kernel, so let me write it down again. So this kernel, so this is a kernel, so it has two, I can consider it as a function of two input vectors, x and x twiddle, and this is just, I'm taking the gradient of my function f theta at the point x, and the gradient with respect to this W, and I take the inner product of this with again the gradient, but now at the other argument. So I take the gradient of f at point x, the transpose of this, multiplied with the gradient of f theta of x twiddle. Okay, and then we worked this out last time. Yeah, I mean, of course, it's easy to do the gradient of this function. This function depends on the W's, and see what the derivative is. And the result, of course, is, yeah, so what is it? I get the derivative with respect to the W's. This means I get the derivative of sigma, and then I get the inner derivative, and the inner derivatives gives me the vector x. So from here I get the x, here I get the x twiddle. So I have x transpose times x twiddle. Okay, and then I have the 1 over square root of m for each of the gradients, or for each of the functions. So I get altogether a 1 over m. And then I have the sum of the gradient. Yeah, okay. And of course I'm taking, I mean, the gradient, this means the gradient is a vector which is given by taking all derivatives with respect to all the vectors Wi, and I'm multiplying this with itself. So this means in this sum from this term here, I take the part where I have the derivative with respect to wi. But of course, this is only one term in the summand, the one corresponding to I, and I have to take here the same term. So I'm summing here over the i's from 1 up to m, and then I take the derivative with respect to wi of this guy times the derivative with respect to wi of this term. Okay, and so what do I get? First of all, I get the ai. This is just a constant now. I get an ai from here, and I get an ai from here, so I get ai squared. And now you see why if I find it nice to have ai squared equal to 1, because ai is just plus or minus 1. Okay, so this will go away, but then I also get the derivative of sigma at its argument, wi transpose x, times the inner derivative, which is x, which I already have here, together with the transpose. I mean, this here is just a real number. There, the transpose doesn't make a difference, but here I get the transpose, and then I also get the same from here. So there I have the sigma prime of wi transpose, x twiddle, and the inner derivative, the x twiddle, is here. Yeah. Okay. So that's just working it out, very easy. And now the simplification. So this is 1 because of my choice of the AIs. Yeah, and then I'm left. Maybe let me write it down again. So what I have here is x t x twiddle, and this is 1 over m times the sum I from 1 up to m. This goes away, and I have sigma prime of wi transpose x times sigma prime of wi transpose x twiddle. Okay, so that's a rigorous expression, which is true for any size m. And now and of course this is a probabilistic object, because those are random vectors. So this is a random number which I get here, but I'm claiming if m goes to infinity, this converges to a deterministic number. Okay, and so why should this converge to a deterministic number? Yeah, because you see what I'm doing here is I'm averaging a sum over m things, and okay, this suggests that maybe we are in the realm of the law of large numbers, for which we would need that those guys for different i's are independent, but that's actually the case. Because I mean the entries, so wi, those are the vectors of my matrix, and all the entries in my matrix are independent. So the w1 vector is independent from the w2 vector, and so on. So this here for I equal to 1 is independent from the same thing for I equal to 2, and so on. So those guys are really independent, and they have all the same distribution, because each wi here is just a Gaussian random vector. It's the same covariance. Okay, so those guys here, they are all independent for different I, and they have for each I the same distribution. And same distribution for each I. Okay, and so this means I have here really IID random variables independent, identically distributed, and then the law of large numbers tells me that if I take the average over them, I converge to the expectation of this. So this means if m goes to infinity, this quantity here goes to the expectation. Yeah, so this 1 over m, let me write here, so this 1 over m, the sum from 1 up to m, sigma prime wi transpose x, sigma prime wi transpose x twiddle, this converges, if m goes to infinity, to the expectation of this situation here, where now, I mean, wi, they have a, let me just, instead of writing w1 or w2, just let me write v. V is just a random vector which has the same distribution as each of the wi's. So I take here the expectation over the distribution of V, and here I have sigma prime of V transpose X times sigma prime V transpose X twiddle. Where this V here has the distribution as these W's, which is just it's just a Gaussian random vector with covariance 1. So V is a normal distribution in p dimensions. It's a p-dimensional vector with mean 0 and covariance 1, which means all entries are just independent Gaussians of variance 1. Okay, so and this here is just the law of large numbers. Good. Okay, and so this shows us how we get here a deterministic object, and with high probability we are very close to this deterministic object if M is large. Okay, and then of course now the neural tangent kernel, I mean the one in the limit, of course this is this guy here, maybe multiplied with X transpose X twiddle. That's what I define now as the limit object, and that is the one which is now the deterministic object which should determine the evolution. So I define now the neural tangent kernel, maybe I call it now K star, as the kernel, which is just given by this. So K star of X twiddle. So this is the expectation with respect to this random vector in p dimensions. And the quantity I take of this vector is sigma prime of V transpose X times sigma prime of V transpose X twiddle. Okay, and then maybe, okay, I should also have the xt X twiddle. Yeah, okay, and then, yeah, by the above, by the law of large numbers, I know that this converges to the limit. Yeah, we can say by the law of large number or just by concentration. I mean, law of large numbers is a kind of statement on concentration, that we are very close to the limit. Yeah, we know that with high probability for sufficiently large M, the difference between this limit kernel and this thing here is as small as we want. Good, okay. And maybe before we look on the time evolution, maybe I want to do an example where we really can calculate here something concrete. So to see what kind of object we have here. And maybe for this, I mean, essentially I have to change to choose now my sigma, my nonlinear function. And for this, let me choose the ReLU function. Of course, strictly speaking, the things I'm doing here, for this I should assume that my function sigma is differentiable, and maybe for later things, for estimates, it should also have maybe twice differentiable or so. ReLU is of course the function which is 0, smaller than 0, and it's just a linear function, bigger than 1. So of course it's not differentiable at 0, but of course, I mean, this doesn't make a big difference, because this 1 point doesn't play a role. So in principle, it does not fit directly into the general theory, but one can calculate by hand what is happening there. And of course, the derivative of the ReLU is very, very easy, so very concrete. So maybe we can calculate this guy here. Of course, it's one thing to have it abstractly, but it's also nice to have it concretely. So I consider sigma, so this is the ReLU function. And then what is the derivative? Of course, on the negative side, ReLU is 0, the derivative is 0. On the positive side, ReLU is just the identity function. T goes to t, and the derivative is equal to 1. So then the derivative of ReLU at a point t is either 1 or 0, depending on t bigger than 0 and t less than 0, and maybe we don't talk about what happens at 0. Okay, and yeah, maybe in the following, we should also consider that the norm of x and x twiddle is equal to 1. That I said that essentially we restrict to this just to make things a little bit simpler. So I also look on the situation where the arguments of my neural tangent kernel have norm 1. Okay, and so what do I have to calculate here? So I should now, for this limiting neural tangent kernel, I should take the expectation of this quantity with respect to a Gaussian distribution. And of course, the function I take here, this is the characteristic function of the argument being positive or negative. And so what I have to calculate is the expectation over my random vector v of the characteristic function. Yeah, what is the argument? In the first sigma prime, it's my vector v is multiplied with the vector x, that this is bigger than 0, times that the same quantity where I multiply v with x twiddle is bigger than 0. So in principle, I have here my Gaussian vector v, and I'm multiplying it with, I take the inner product with two vectors, x and x twiddle, in the same p-dimensional space, and I want that both those inner products are positive. And I want, this is the probability that this happens. Okay, but the question is, what is this? This is not a priori clear what this is, because we want this for all x and x twiddle. If x is equal to x twiddle, then of course it would be just one condition, then it would be somehow easy. But if I have those two conditions, maybe, it's a bit unclear. So, but maybe one should note that, of course, the entries of v are independent Gaussians, and if I multiply it with x, I take a linear combination of those independent Gaussians. So this thing here is just a one-dimensional Gaussian distribution. And this here is also one-dimensional Gaussian distribution. So I have here two Gaussians which have a given covariance. Okay, so what I get here, those two guys, they are actually two Gaussian vectors with a given covariance. And what is this? So note. That is what we already did somewhere in the assignments, or so, that if I have independent Gaussians and I do transformations on them, I also get new Gaussian families where I get a changed covariance structure. So here I get, let's say 2, maybe I call this T1, this is V transpose times this, and T2, this is V transpose X twiddle. So those are two Gaussian vectors with a covariance sigma. So the covariance between them. The variance of each of them. The variance of such a linear combination is just the norm of this guy, or the norm squared. Okay, but the norm of those guys we have said is equal to 1. So the variance of each of them is equal to 1, and then the covariance, so this means the covariance between this and this guy, this is given by the inner product between x and x twiddle. That's again something we know in principle, and maybe I call this, let me say I call this alpha. So I put here alpha, where alpha is x transpose, so the inner product between x and x twiddle. Okay. So in particular, if x and x twiddle are orthogonal, then of course this is 0, and I'm just getting two independent Gaussian vectors. If they are not orthogonal, I have somehow a mixture, and there's a given covariance there. Yeah. Okay. So what I have here are two Gaussian vectors with a given covariance structure. And we know the density of such a situation. It's a Gaussian density of random Gaussian vectors with a given covariance. And in this covariance, we need the inverse of the sigma, which of course is very easy to calculate here. So the sigma to the minus 1. So this is 1 divided by the determinant, which is 1 minus alpha squared. And then I just get here 1 minus alpha minus alpha. Okay, and then the density is the following. So the density of this two-dimensional Gauss is 1 over, square root of 2 pi to the dimension, but this is now 2, so I have 2 pi, and then I have the determinant of sigma to the 1/2, and then I get here the exponential of, minus 1/2, and I have here the inner product between this vector and itself, but modified with the inverse of sigma. So what I have here is T1, T2, and here I have sigma to the minus 1, T1, T2. So that's the general formula for the density of two-dimensional Gaussian random vector with a given covariance matrix sigma. Okay, but now of course we know what sigma is, so I can write it down explicitly. And this is now, so this is 1 over 2 pi, and the determinant of sigma is 1 minus alpha squared, and I take the square root of this, so I have 1 minus alpha squared, the square root, and then the density is this inner product. So I multiply T1, T2 with this guy here, so I get here a linear combination, so I get T1 minus alpha T2 and minus alpha T1 T2, and I take the inner product. So what I get here is minus 1/2 T1 squared plus T2 squared. This would be the part if sigma would just be diagonal, if my two Gaussians would be independent, but of course they are not independent, but I get here this covariance part, which is minus 2 alpha T1, T2 divided by 1 minus alpha squared. Good, okay, so that's the density, and what we have to check is, or what we want is the probability that both T1 and T2 are positive, because that's what we want here. We want this expectation over this characteristic function. So this is the probability that this guy and this guy, so the T1 and the T2, both are positive. So in principle, I have to integrate this density over the part where T1 and T2 is positive, and that would be the answer. So our expectation with respect to V of this quantity would just be the integral over this density, psi1, psi2, dt1, dt2, but only over the positive part. So this means I'm integrating only from 0 to infinity for both of them. Okay, and without this coupling, of course, this would be very easy. If they would be independent, then this would be clear. Then it would factorize into the probability for each of them. And for each of them, of course, the probability that it's positive is just 1/2, because it's symmetric. But now they are coupled somehow. And of course, one can calculate this. This is just an integral. One can do some change of variable, and you can calculate it somehow. But actually, maybe one can also think a little bit and argue more directly, calculating this integral without really doing explicit integration. So maybe I want to give a kind of argument which gives us the answer without having to do these integrals. Okay, so what we have here, so what we have here is essentially we want this probability that for given x and x twiddle, those two projections of our Gaussian random vector both projections are positive. Okay, and in principle we can, this random vector here is in R to the P, but already here we went down to R2 because the problem essentially lives in R2 because we are looking on those two combinations. And in general, you can just say, instead of looking on the V in R to the P, I just look on the projection of what is spent by x and x twiddle. because it's really, I'm just projecting it down to the plane which is spanned by x and x twiddle. And then things are the projection of Gaussian things is again a Gaussian thing. So essentially I can assume that I'm living here in 2 dimensions. So that my V is just a 2-dimensional thing, and this is also a two-dimensional thing, which essentially also was there. So I can assume, okay, so this is not calculating this, but more directly giving an answer for this. So we assume that all my guys, so the x and the x twiddle, are actually in R2, and the V is also in R2, and it has a normal distribution there with independent components. Okay, and so what I have to do, I'm now in R2, I have a Gaussian random vector there, and I have 2 vectors which are fixed, and I want to see that the projection on each of them, or the inner product, is positive. So what I want to check for each of the 2 is whether the inner product of my Gaussian random vector with the given x is positive. Okay, but actually for this being positive, taking the inner product with my Gaussian random vector, I can also normalize this to 1. I mean, I'm here in somehow in 2 dimensions, and I have my random vector v, which shows in 1 direction, but actually for checking what is the inner product with a given vector x, I mean my vector x has norm 1, I can also normalize this to equal to 1. So I can somehow project my Gaussian random vector just onto the circle of radius 1. And of course, if I have a Gaussian random vector, I mean this distribution is Gaussian. But if I just want to know what is the distribution of the normalized Gaussian random vector on the unit circle, of course this has a uniform distribution. I mean Gaussian random vector is rotational invariant, so this means the distribution of the normalized vector, my Gaussian random vector on this is uniform. So that's easy to control. And for checking what I want to know, instead of checking for the full information about my Gaussian random vector, it's enough to check for the normalized version. So this bigger than 0 is the same if I take the normalized version of my guy bigger than 0. Yeah. Okay, but this means instead of arguing with a Gaussian random vector, I can now argue with this vector here, which just has a uniform distribution on the unit circle. So we can replace V, which has a normal distribution in 2 dimensions. I can replace this by Vt divided by its length. Of course, I want to divide by V. Yeah, I normalize the vector V. Okay, so I replace this by Vt, normalized by V. So this is now a vector of length 1, which lives on the unit circle, but the distribution of it is just a uniform distribution. So this is by this, which has the uniform distribution on the circle. Okay, and so now my problem is I have given 2 vectors, and then I want to know the probability for a uniformly distributed vector on the unit circle that the inner product of this with each of the 2 is bigger than 0. So we want this for all x and x twiddle. They are given, but they can be anything. So what we want is the probability of this vector on the unit circle, and maybe let me write it as e to the I phi. So this is my vector on the unit circle, or the torus. And what I want is that the inner product of this vector with the given x should be bigger than 0. And at the same time, this inner product of this e to the I phi with x twiddle should be bigger than 0. Okay, and now we just have to think. So I have this vector on the unit circle, and I want to satisfy those conditions. But I mean, what are the phi for which such a condition is satisfied? I mean, if I have a vector x, and I want to know for which phi's is it true that e to the I phi x is bigger than 0, then of course, I mean, I take here the perpendicular direction, and all the phi's which are here, they are okay. I mean, that's, if I have a vector within this range, then of course the inner product with this is positive. If I have on the other side, it's negative. And I have this for x. And of course I also have this for x twiddle. I mean, x twiddle is a different vector which shows in a different direction. And for the x twiddle, I mean, everything which is in this range is okay. So those phi are okay. And now I have to check what is the, which are the phi's which are okay for both of them. So now I have, I mean, I have my both vectors. I have the x and I have the x twiddle. And then of course for the x, I mean, the range where it is okay is I take the perpendicular direction, and for the x twiddle I also take the perpendicular direction. And now, what is okay for both of them? This is, of course, what is between those two lines here. Yeah. Okay. So this is the range which is okay. So I mean, starting here from the one which is perpendicular to this, and ending here which is perpendicular to this. Okay, and how big is this? This, of course, depends now on the angle which is between x and x twiddle. So I mean, if I go from here to here, this is 90 degrees. If I go from here to here, this is also 90 degrees. Okay, so if I'm adding this up, I get 180 degrees, but then I have counted beta twice. So this means this range here is pi over 2 plus pi over 2 minus beta. Okay, so so the range of everything here. So this here is pi over 2 plus pi over 2. But then I have counted beta twice, so I should subtract it. So that's the range of angles for which both conditions are satisfied. And of course, this is pi minus beta. Okay, and because I want the probability, I have to normalize it by 2 pi, because 2 pi is the whole angle of the circle. So the probability I'm looking for, this is just pi minus beta divided by 2 pi. Yeah. Okay, and of course now I should express beta in terms of x and x twiddle, but of course this beta is connected with x and x twiddle, because the inner product between x and x twiddle is the length of x times the length of x twiddle, which is 1 times the cosine of the angle in between. So beta is actually the arc cosine of the inner product. So we have the inner product between x and x twiddle. In general, it's the length of them times the cosine of the angle between them, and the angle, that's what beta is here. So those guys are 1. So this means beta is the arc cosine of the inner product x transpose times x twiddle. And so we see that our probability, which determines the kernel, I mean, what we really want is this kernel, but now we calculated this by just this quantity here. And of course, if you do the above integration just by change of variables and this, I mean, you should also arrive at this one here. Okay, but this, it's a nicer geometric argument, so you can get the result without having to do hard work. But you need some soft ideas. Good, okay, so this means our kernel in this case, x twiddle, so this is x transpose x twiddle, and then we get this probability here. So this is pi minus arc cosine of yeah, xt x twiddle divided by 2 pi. Okay, so I think this is a nice concrete calculation which shows that, I mean, one really can calculate, at least in concrete situations, this kernel, and you get something concrete which you then can also use for doing other calculations. Good, but maybe we should now come back to the question of the time evolution of this kernel. So this here was at initialization. I chose my W's in a random way, and then we saw that the corresponding kernel, this neural tangent kernel, is close to the deterministic object. But then we do the training, which means we are changing the W's, and the statement was that this kernel does actually not really change. So that's maybe that's a kind of surprising statement, maybe something which maybe we should understand a little bit better. And so I want to do now going a bit in this direction to that we see how such a thing can happen. Yeah, so we look on the evolution of the kernel under the training, and yeah, the statement that this does not change or does not change much depends essentially on the fact that the weights are not changing much. So we are updating the weights, but actually they're not really changing a lot. So we should look first on the evolution of the weights, of the W's. Okay, so for this, recall how our training worked. So we had that the time change of our parameters, and this is the W in our case, this was given by the gradient of the loss function. So this was, in general, the gradient with respect to our parameters of the loss function, which depends on our parameters. And I also had an eta there, but maybe I just put this here equal to 1. Doesn't make a big difference. Okay, and the loss function, this was the sum of the square of the differences between f evaluated at our data points xk and the target values which they should have there. Okay, and of course we can take the derivative of this. So what this was minus, and we are summing over the training data. So we have n data points, and there we have essentially ft xk hat minus yk hat. So the loss function was the square of this divided by 1/2. So we take the derivative, so we get this, and then we get the inner derivative. So we get the derivative of this guy, which then gives us the gradient of the function f with respect to the parameters. So we get here the gradient with respect to theta of ft applied at the points xk. Good, okay, and then we calculated the gradient of f theta. That is exactly the quantity which we got there, or essentially that was half of it. I mean, the kernel is this gradient multiplied with itself, and so this quantity here, so of course this was, maybe let me write it here, and let me just write it down for theta is now the wi. I mean, our parameters are now all the entries of w, but I collect them into the wi's. So the gradient with respect to wi of ft of applied to xk twiddle. So this was just this ai times sigma prime of w transpose xk hat, and then the inner derivative. This is the xk hat, and of course I have a normalization there. This 1 over square root of n. Okay, so that's the gradient. Good. Okay, so this means for our wi's. Let me write down again what we have here. So the derivative of the wi, which of course depend on the time. The wi's, the parameters are now depending on the time. They are functions of the time. So what is this? This is this 1 over square root of m, sum over k from 1 up to n. Then I have this difference ft of xk hat minus yk hat multiplied with this one, and this is ai, and sigma prime of wit xk hat times xk hat. Good, so that's the time derivative, which governs the evolution. And now we want to see how much does our weight change, let's say if we go from time t, or from time 0 to time t. Okay, and we want to estimate this and to see that this is somehow of small order. So if m is going to infinity, this should go to 0. This means in the limit, the weights actually don't change anymore, which, yeah, is a bit strange, but that's what happens here. Okay, so consider the evolution of the weights. So what I want is I take, let's say, the weight at time t minus the weight at time 0, and I want to see how much has this changed. And because I have the differential equation, so I know the derivative of the change, so I just calculate the change from 0 to t by integrating the derivative of the change. So this is the same as integrating from 0 to t of the change of the weight maybe here I'm right, no, right tau. So okay, yeah, good. Okay, and so I take here the two norm. So I mean the w's, each of them is a vector, so I consider their Euclidean norm, which, okay, I mean I could put a 2 there, I could also leave it away, it should be clear. It's this one. Okay, and now of course I have, for this derivative, I have this equation here, so I can plug this in. So what I have here, so this is the norm of the integral from 0 to t, and now this time derivative, this is 1 over the square root of m times the sum from 1 up to m. Then I have this ft of xk hat minus yk hat. So that's somehow the driving force. If I have not achieved the right value at the points xk's, I mean I want to change the weights such that things are getting better. Okay, and then I have the ai times the sigma prime of wi transpose xk hat times xk hat. Okay, and I want to take this here, the 2 norm of this. Yeah, now what is the order of the whole thing? So we want really to understand how does this depend on m and n and such things. Okay, and so what do I have here? I mean here I have this difference, so this should be of order 1. So I mean, okay, I mean those are just real numbers of order 1. They are not changing somehow with m. I mean, and also this here should be close to this, so this should be something which does not really depend on m or n or whatever. Okay, then the ai is just plus minus 1. Okay, and so here I have the sigma prime of an argument, and this argument, yeah, so what is this argument? This is of course a Gaussian variable. I mean, the entries of the wi are independent Gaussians. I multiply them, I take a linear combination of them with with the coefficients of this vector x. And so what I get is this is a Gaussian variable which has the variance of this xk. So this is a Gaussian variable of variance, which is the norm of xk hat squared. Okay, but let's say they are also have also length 1. So our data points are also normalized to have length 1. Okay, so the sigma prime is a function which should be differentiable. So this should be a nice function, and the Gaussian variable here is in principle of order 1. So this here is also the sigma prime is also something which is of order 1. So I'm so everything I have here is of order 1. So what I have here, of course I can say this is less or equal. I can bring out the 1 over square root of m. I can bring out the sum from m, and then I'm left with the integral of the absolute value of those guys, but everything which I have here is of order 1. So I'm integrating here things of order 1 with respect to dt. Yeah, and then of course, so I'm integrating here. This integral will then be of order t. So what do I get? So I have here the order which I get in my quantities. This integral here, order 1 times t. So this is t. Here I'm summing over m terms, but I'm dividing by 1 over square root of m. So I get here an order, I get here an m divided by square root of m. So I'm dividing here let me see. So I have here no. The summation here is running to n. Okay. Okay. So n is the number of data vectors which I have. Those are the x1 head up to xn head. I take n observations, so the summation here is going up to n, and this 1 over square root of m. So m is the number of features which I have in between, and this is what I want to send to infinity. Okay, so I have here this 1 over square root of m. This is just here, and this summation here, which goes to n, gives me a factor n. So the order which I have here is t times n divided by the square root of m, and so this means if I'm sending m to infinity, then this goes to 0. But you see, I should keep n fixed. The arguments I'm doing here are essentially for the setting where n is fixed, or this divided by this should go to 0. So one has to be a bit careful which regime one is considering. But that's what is meant here in this context, is that in the white regime, the kernel is not changed anymore. This is really meant in this way, that m is going to infinity, but n is kept fixed, or has a much smaller order than m. Good, so this means that the weights are not changing much. In the limit, actually, they don't change at all, but so that they are not changing much. And this, of course, now means that essentially also the kernel, the change of the kernel is determined in terms of the change of the weights, that this is also not changing much. So this here is the main, that's somehow the reason why the kernel is not really much changing, because the weights. We are training the weights, and of course in a finite situation we are changing them a little bit, but they are not changing much. So essentially we do an initialization. This means then we get some weights, and then we train them, but essentially we always stay very close to from where we started. And the kernel which we calculate actually is more or less the kernel which we had at the beginning. So in a finite situation there is a small change, but not much. And actually in the limit, in principle, nothing is changing anymore.